Hello and welcome to 6.3 as we tackle a little bit more about trig functions. So we talked before about the idea of SOHCAHTOA on a right triangle. In advanced trigonometry, we basically talk about that idea of a point being at a coordinate xy. That's on the edge of that angle that's in standard position. Once you have that point, you can always, every single time, construct a triangle going down to the x-axis, which will give you both the x value to get that far over and the y value to get that far up, with that just being r out of convenience. You could say it's part of a circle if you really want. Once you have this triangle made with x, y, and r, you could then redefine all of your trig words based off x, y, and r. This is an optional technique to talk about the idea of SOHCAHTOA applied in more sophisticated ideas, but you can still use SOHCAHTOA if that's more comfortable. Once we introduce this idea, then the concept of location gets a lot easier. We talked about in the last class this concept of being in quadrant 2, so x is negative. Once you account for that, you can actually worry about where all functions are positive or negative. You could refer to this as all students take calculus as to who's positive in those functions. Those quadrants. Once you know what functions are positive, you could then use the fact that sine is matched up with cosecant to be able to figure out what the other one would be. So let's do some quick calculations. The secret to this is to come up with a really good reference triangle. So this 225 spins around that far. You might remember from our Kahoot, that was 45 degrees past 180. That 45 means that this could be an a root 2, or out of convenience, I can refer to this as a 1, 1, and root 2, just letting a be 1. Because I'm down here in quadrant 3, I would make both the x and the y negative. So now my sine of 45 degrees would be the opposite of our hypotenuse. So I can kind of switch skills there, and I can recognize it as negative 1 over root 2 or negative root 2 over 2. Cotan, I can follow the same idea. 360 spins all the way around, and I can say that that's going to be coterminal with 120. 120 would fall out here, being 60 degrees short of the 180. Once I know that's a 60, I can call this a root 3, and call that a 1, and call that a 2. Because I'm in quadrant 2, I put a negative. Personally, I don't favor the all students take calculus strategy. I prefer to make my x and y positive or negative based off the quadrant, and then let the answer be what it is. Alternatively, you can do the whole problem positive, and then apply the all students take calculus to decide whether or not it should be negative. My tangent would be root 3 over negative 1, so my cotangent is negative 1 over root 3. Which of course can be rationalized. So pretty much the same game. 5 pi is a little bit awkward because it's quadrantal. 2 pi is 1 lap. 4 pi is 2 laps. And then an extra pi has me end out there. This also is a great time for this xy argument. If you try and use SOHCAHTOA with the dot directly on an axis, you don't really have a triangle to work with. So you don't really have an opposite and an adjacent per se. But if we think about the cosine as being the x value over the r value, my x value is negative 1 and my r value is 1. R being like the a value of the scale of my triangle. And then over here I got 14 pi over 3. I don't know where 14 thirds is off the top of my head, so I'm going to kind of think about this instead as dividing each region into thirds. 1 third, 2 thirds, 3 thirds, 4 thirds, 5 thirds, 6 thirds, 7 thirds, 8 thirds, 9 thirds, 10 thirds, 11 thirds, 12 thirds, 13 thirds, 14 thirds. It's going to have me stop there. That same triangle is the same triangle we did before, with a third of 180 being 60. Got a root 3, a 1, and a 2. Cosecant is going to be sine upside down. So sine would normally be root 3 over 2. This is 2 over root 3. You're also more than welcome to either go coterminal and keep subtracting 2 pi's until that gets more comfortable, or switch it to a degree and then keep subtracting 360s until that gets more comfortable. Either way works. It's really just a matter of preference. Negative angle, remember with our standard position that's actually swinging underneath. I could use the same argument of cutting this in fourths and going with 3 of them. This is pi over 4 or 45 degrees. So I know that this is going to be a negative 1, a negative 1, and a root 2. My tangent is -1 over -1, so it automatically works out to be 1. I don't need to worry about the sign separately. 720 is going to be 360 to go one lap, and then another 360 to go a second lap, and again I get one of these special case quadrantals. This coordinate is going to be an x value of 1, a y value of 0. Secant is going to be the cosine flipped upside down. My cosine would be 1, 1 flipped upside down is 1. This is going back to that idea of the pairing of sine and cosecant. Once you get comfortable with this pairing, you can always just flip them upside down. You could either flip the opposite over hypotenuse upside down, or you could actually flip the function upside down. Cosecant is actually the same thing as 1 over sine. Same goes for these other special functions, and then we also get the definition of tan as being sine over cosine. We also have these Pythagorean identities. Those are going to play a small role right now, but they start to play a much bigger role later on in Chapter 7. Alright, so again we get one of these tan setups. They tell me that I'm in quadrant 2. It's helpful because I know tan is negative in 2 different spots. So them telling me I'm in quadrant 2 is important. I know that my tan of this angle, which is really that, but I'm calling it inside the triangle, is going to be my opposite over adjacent. Now if I mark that directly as it is, that's really silly because clearly the root 3 is not negative. So the negative actually was supposed to apply to the 3 on the bottom. I can do a little bit of Pythagorean theorem to find that top, and I can say root 3 squared. I could say -3 squared or positive 3, because I'm going to square it, it really doesn't matter. 3 plus 9 equals c squared. C squared is going to be 12, which we could reduce to be 2 root 3. My cosecant of this problem is going to be the adjacent over the hypotenuse. Remember, I can rationalize that top and bottom by root 3. The 3 times the 2 would end up being 6. 3 and the 6 could reduce. And I get that. Pretty much the same problem. I'm hanging out in quadrant 4, so I'm going here. Remember, we always go to the x-axis. Technically, that is my angle, but I'm just going to kind of pretend it's that one. Trig doesn't care. My secant is going to be whatever my cosine is flipped upside down. So my cosine of that angle is going to be 3 over 2 root 3. I can rationalize that in advance. As we saw in class, that usually makes the problem a little bit easier. And that's going to give me a 3 root 3 over 6, and that reduces again. I get a root 3 over 2. So my cosine is going to be a root 3, my hypotenuse is 2. Look at that. That's a 30, 60, 90 triangle. Not that it's important in this problem, it's just nice to note. And then I could list off my 6 trig from there. I'm a little short on time with this presentation, so I'm just going to leave that to you. Alright, this is a tough one. I'm assuming I'm in quadrant 1. That's all I read about the problem. I know this is true. I'm going to try and write the sine value in terms of the cosine value. Now we saw in terms of as being a really nasty phrase. I need to find an equation that links sine and cosine. If I just tried to base it off my opposite and my adjacent and my hypotenuse, sine and cosine do not touch. I can't get a single trig that has 2 different trig words in it, so I need to be more creative. Luckily, early on in the presentation, we saw the Pythagorean identity, sine squared of theta plus cosine squared of theta equals 1. That's one equation that has both of the things I care about in it, so that's exactly what I want. I want sine theta in terms of, so I need this sine to be alone. Juggling my algebra a little bit, I can subtract that cosine squared over, and then of course I can take the square root of that. Now, I know I'm supposed to have plus or minus in front of the square root, but I want to remember what the problem told me. The problem told me I'm in quadrant 1. If I'm in quadrant 1, the result of sine should be positive. So I'm going to purposefully not put the plus minus out in front, because that minus would imply this triangle down here. That's not the one I want to talk about. Same game, hanging out in quadrant 2. Quadrant 2, I'm trying to get cosine and cosecant teamed up. Now if I go back and I look at that slide, there is no formula that has cosine and cosecant in it, so I might need to be a little bit more creative. Cosecant is based off sine. So if I start with that same identity, I can then take that sine value in the problem and switch it into a cosecant value. This is not necessarily a good thing to do. It's not something that makes the math easier, but it's what the problem asked for. Because the problem asked for it, I have to adhere to those specifications. I want cosine to be alone, so I'm going to pretty much do the same trick I did last time. Algebra paths may vary a little bit here. Let's go ahead and get rid of that too. And with a quick quality control to decide whether or not cosine should be positive or negative at this time. I look at this as negative x values, so therefore my cosine should be negative. You also could remember it as all students, which means that sine should be the only thing positive in that quadrant. Pretty much the same thing. Hanging out over here, if my cosine is negative 2/3, that means that this is negative 2 and that's a 3. If we're looking for a tan, I could say a squared plus 4 equals 9, so it's going to be the square root of 5. Now that I know that's the square root of 5, positive because it's going up, I can say that the tangent of theta is going to be root 5 over negative 2. Let's cut off a little bit, but that's supposed to say greater than 0. This is tricky. I'm trying to figure out a quadrant where those things should be greater than 0. If that's greater than 0, one of two things could happen. I either have a positive times a positive, or I have a negative times a negative. I could do a little quick analysis and figure out what's the story with tan. Tan is positive here, negative there, it goes positive again there, and it goes negative there. Again, thinking back to that slide where all students take calculus. Cosecant is based off sine. Sine is positive here, negative there, and negative there. If these things are multiplied together and I want them to be greater than 0, that happens in both of these spots. So it's true in quadrant 1 and quadrant 4. Alright, that's all I got today to talk about 6.3. Hopefully it made some sense, and you get to enjoy your night off.